have a look at page 8, Mark 16P42. Define what is capacitance. Wait on, let me have to open up the question. Mark 16P42. Question 7. Okay, define capacitance. This one is just a 1 mark question. So since it's just a 1 mark question, you can just say it is the ratio of charge to potential or potential difference. Okay. Now the ones that I've just written in pencil here, it is a charge flow at one plate of the capacitor per unit PD applied across the 2 plates of the capacitor. This one is more for 2 marks. Okay. This one is used for capacitance of a parallel plate capacitor. Okay, capacitance of a parallel plate capacitor. Okay, you normally reserve this definition if they ask you to define capacitance of a parallel plate capacitor, and usually it will be worth 2 marks. Okay, so this one I don't suggest. I don't think you should write this. This one is reserved for this. Capacitance, this one is asking you capacitance in general. Okay, and usually it's worth 1 mark. When they ask you capacitance in general and it's worth 1 mark, usually you use this definition. It is a ratio of charge to potential difference or ratio of charge to potential. C is equals to QV, right? So it's either ratio of charge to PD, or is ratio of charge to potential. Okay, it doesn't matter which one you use, both are accepted. Okay, so this one should be the correct one that you use. Okay, ratio of charge to potential difference, or ratio of charge to potential. The ones that I wrote in pencil, this one not really suitable to be used. You reserve this for 2 mark questions which talks about parallel plate capacitor. We will have a look at that later. Okay, so this one just say is ratio of charge to potential difference, or ratio of charge to potential will do. Okay, then you look at the part B. 3 capacitors or capacitances C1, C2, C3 are initially uncharged. They are then connected in series to a battery as shown in figure 7.1. The battery applies a potential difference V across the 3 capacitors. Show that the combined capacitance C of the capacitors is given by this expression. These are capacitances connected in series. So for capacitance connected in series, the form of the capacitances is similar to resistors in parallel. I mentioned that the form would be the direct opposite, isn't it? So you see this one is in series, you know that it should be similar in form to resistors in parallel. So it should be 1 over C equals to 1 over C1 plus 1 over C2 plus 1 over C3. And they're asking you to derive this expression now. Okay, so based on what I mentioned to you, you normally always try to single out the voltage and charge. You look at it either in terms of the voltage, or you look at it in terms of the charge. Usually it's either these two. You always start with either these two. Now for your case here, you see this one here. If this one is V, this one is V1, this one is V2, and this one is V3. V is actually V1 plus V2 plus V3. And then C is equals to QV. I can replace out V. I want to replace out V. So V is Q over C. This becomes this now. Okay. Then after that, as I mentioned to you just now, whatever charge that flows out will be the charge seemingly stored here, will be the charge seemingly stored here, will also be the charge that is seemingly stored here. Okay. So Q1 is equals to Q2, Q3. Wait, this one I think I better rewrite it. This one you can write it as this Q1, Q2, Q3. Okay, so Q is actually Q1 equals to Q2 equals to Q3. So therefore, QC is Q over C1 plus Q over C2 plus Q over C3. Then it becomes this. Okay. If you want to write it out step by step, this one should be the correct one. Okay. So total voltage is V1, V2, V3. It becomes QC, Q1 over C1, Q2 over C2, Q3 over C3. But whatever charge that flows will be the same charge that is seemingly stored in 1, 2, and 3. So Q equals to Q1, Q2, Q3. Then it becomes this. Then after that, you can start cancelling them off, giving you this. Okay? So that one is for this. Then after that, I will move on to the other part, if you're okay with that. Right? Okay. Now, you have a battery of EMF 12 volts and negligible internal resistance connected to a network of 2 capacitors and a resistor as shown. The capacitors have capacitances of 200 microfarad and 600 microfarad. The switch has 2 positions A and B. Now the switch is moved to position A. Find out the combined capacitance of the 2 capacitors. Your switch can either be at A, it can either be at B. Now they tell you that your switch is at position A. If your switch is at position A, it looks like this now. Okay, your circuit looks like this now. Your 200 microfarad and 600 microfarad here. They ask you to find the total combined capacitance of these 2 capacitors. This one is capacitors connected in series. So you know that the form of its expression, combined capacitance, will be similar to resistors in parallel. Okay? So series is parallel, parallel is series when it comes to capacitors. So this one is connected in series. So you expect the combined capacitance to be similar to resistors in parallel. So it will be 1 over C equals to 1 over 200 plus 1 over 600, giving you 150 microohms. Okay. CT here is total capacitance. All right. You can also write it as C lah, up to you. Okay, it doesn't matter. Right. So your combined capacitance is 150 microfarad. Okay. So from there, they then ask you, find out the charge on the 600 microfarad capacitor. Okay. They want to find out what is the charge on the 600 microfarad capacitor, which is this one here. Okay. So how do you find that charge? Okay, usually for capacitance questions, it is usually good to draw the diagram and then simplifying it after that. Okay, to do the questions that has capacitors, it is usually best just to draw the diagram first and try to simplify it as much as possible. It'll make your workings much easier to understand. Okay, now this circuit here, I can simplify the 2 capacitors into a single equivalent capacitor, which is 150 microfarad. Okay, now this is the same circuit simplified as much as possible. Now for this circuit here, I know that the total PD is 12 volts. Yeah, I know that the total PD is 12 volts, and I know the total capacitance is 150 microfarad. I can find out what is the total charge that is stored in the entire circuit. Now, whatever charge that is stored in the entire circuit will be the charge that is stored in the 200 microfarad capacitor. It will also be the charge stored in the 600 microfarad capacitor. Okay, so I work with this one first. Okay, I want to find out what is the total charge stored. whatever total charge is stored is actually the charge stored here as well as here. Okay, so that's why your working here is like this. This is you applying C equals to Q over V for the entire circuit to find out the total charge. Okay, the total charge that is stored is also the charge on each of the capacitor. It will be the same charge at the 200 microfarad. It will also be the same charge at the 600 microfarad. Okay, how do I know that the charge is going to be same? Is you need to look at this diagram. Okay, if I simplify this as much as possible, whatever total charge that flows here is the same charge here, is the same charge here. Okay, so you get the answer as 1.8 times 10 power minus 3 coulomb. Right, so far so good. Then from there, they ask you what is the potential difference across the 600 microfarad capacitor. Now from here, they want you to find out the PD across this side. So this is where I mentioned to you, you cannot just simply say that the PD here is actually 600 over 600 plus 200 times with 12. This one is 12 volts, right? Okay, you cannot use this equation. You cannot use the potential divider equation for this one. You cannot solve it like this. All right, as I mentioned to you, the reasoning was because C is not proportional to V. C is inversely proportional to V in the first place. So you cannot use that same relation. So you have to do it another way. In your current case here, you already know the charge stored, you already know the capacitance. You can actually just apply C equals to Q over V for this capacitor itself. Since you already know the capacitance, since you already know the charge stored, seemingly stored. So you apply C equals to QV for that capacitor itself. 600 microfarad is 600 times 10 power minus 6. Charge stored was 1.8 times 10 power minus 3. You take this divided by this, you're going to get your potential difference as 3. Okay? So then you have your answer. Okay? So this one is the most straightforward one. Okay, so if you're okay with that, then we move to the last part. Now they tell you the switch is now moved from position A to position B. Calculate the potential difference across the 600 microfarad capacitor when it has discharged 50% of its initial energy. Now when your switch is now moved to position B, it looks like this now. Okay, you're interested in this portion here. Okay, now when you were at position A, originally, your charge will start to flow from your power supply, and the charge will be seemingly stored here and here, such that your capacitor will become fully charged. Okay, then after that you switch to position B. This capacitor is no longer connected to your power supply, but it's already fully charged. Okay, this capacitor is fully charged already as a result of it being in switch position A. So your capacitor now being fully charged will now start to discharge through your resistor. It will start to release charge through your resistor here. Okay, so that's why they tell you now the switch is now moved from position A to position B. Calculate the potential difference across the 600 microfarad capacitor when it has discharged 50% of its initial energy. So this one was your capacitor, the 600 microfarad capacitor when it was fully charged, and then this is your resistor. Once you go to switch position B, your capacitor will now start to discharge through your resistor. Okay, you have current flowing. Okay, so when it starts to discharge this current flowing, your capacitor here is actually losing away its charge. It loses its charge, you will lose its energy. So they tell you now what will be the new potential difference across your capacitor here once it has discharged. 50% of the initial energy that it had. Alright. Now energy of your capacitor, you know that there are three equations to it. E is half Q over V, half CV squared, or half Q squared over C. So basically what they're telling you here is your final energy is half your initial energy. Okay? So you can just say it by using this one. Half CV final square is equals to half of half CV initial square. Alright. Now your initial PD for your 600 microfarad capacitor you've already found here. You found it as 3. Okay, your initial value is 3 volts. Okay. As you start to discharge through your capacitor, you lose energy, you lose charge, your PD will start to drop. Okay. So capacitance value does not change. The C and C are the same, they will cancel off. So eventually you get this. You get Vs squared equals to half Vi squared. You solve, you get your Vf as 2.12 volts. Okay. Now this one you can also do it this way. You can say this C being constant here, it won't change. I mentioned to you that capacitance value will not change, just like the resistance of a fixed resistor. Only the charge, only the voltage across it will change, not the capacitance. So here C is constant. You will see that E is actually proportional to V squared. So E2, E1 is V2 squared, V1 squared. E2 is actually half of V1, E1. Then V1 was originally 3. So you get V2 squared. So eventually you still get back the same answer. This and this will cancel. You get 9 times 0.5. Then you square root it, you get back the same answer. Okay. This is one way of doing it. This is another way of doing it. This is by using ratio. Okay. You will get back the same answer. So here the important thing to know is that capacitance of capacitor does not change. Only the charge stored and PD will change. Okay, so this is the important thing to know. Capacitance does not change. Only the charge and PD will change. All right. Now, in your case here, I use E is half CV squared. Right. You generally would not use half QV and half Q squared C because here, okay, now like in your case, if I wanted to use E is equals to half QV, the problem that you have here is that the Q after discharge is unknown. So I cannot use this. This one is what I want to find. Find V after discharge. Yeah, that is what I want to know. But the Q after discharge is unknown. You have the charge before this, but this is the charge before discharge. If you wanted to find out the potential difference across the capacitor after it has lost 50% of its energy, and you want to use the exact same method as this, but the only difference here is that you wanted to use half QB, you will get stuck because here the Q after discharge is unknown. So this one you cannot proceed. Alright. And then for the third equation here, you cannot proceed also because you also still have the same problem where the Q after discharge is unknown. And another thing here also will be that this expression does not have your PD. You want to find the voltage now, the PD, but here this equation doesn't have PD. So it's pretty pointless to use this equation also. So the best one to use will be half CB squared. Alright. So this one is okay. So this one is page 28, was it? No, this one is page 8. Okay, so if you're okay with this, then you look at page 28. Okay, we'll just do this before we go and have a short break. Have a look at page 28. Okay, now they tell you have a capacitor that consists of two parallel metal plates separated by an insulator. The insulator is your dielectric. Okay, now suggest why when the capacitor is connected across the terminals of the battery, the capacitor stores energy but not charge. Alright, this one is June 17 P42. Okay, June 17 P42. Questions? Okay. So, as I mentioned to you before, you cannot, in the formal definition of a capacitor, you do not say that it stores charge. Okay, it only seemingly stores charge. It is not actually storing charge, but it is storing energy. So your question here is asking, why is it that your parallel plate capacitor is storing energy but not charge? Okay, now it will be helpful to refer back to that little diagram. If this is your capacitor and this is your power supply, if I tell you a charge of negative Q comes out from the negative power supply and gets deposited onto one side of your plate, this plate will become negative Q, right? If you have negative Q being deposited on this plate will become negative Q. But at the same time, this negative Q will be repelled off the other plate. Okay? This negative Q will be repelled off the other plate. Now, when this negative Q is repelled off the other plate loses negative Q, so it becomes positive Q. Wait, let me just change a different color for this. This one will be negative Q. This one will be positive Q. Okay, so to reiterate what I just said, when you're starting to charge on your capacitor, charge will flow from your power supply to your capacitor to charge it up. If say a total charge of negative Q comes out, it will be deposited at one side of your plate, causing your plate to gain a charge of negative Q. But at the same time, that same charge that was deposited here will be repelled off the other plate. So because this plate has lost this negative Q, it becomes positive Q instead. Okay? So in other words, this side gains negative Q, so this plate becomes negative Q. This side loses negative Q, so it becomes positive Q. So when you look at it now at the capacitor itself, there's no net change in charge or no net accumulation. no net change. Maybe I better write this bigger. You can say that there's no net change or accumulation in charge. There's no accumulation in charge here is because here you got negative Q, but you also lost positive Q. Sorry, there's no net accumulation simply because of this. You gain negative Q here, but you also lost negative Q here. So there's actually no net change or no net accumulation of charge. Okay. Here the question, your answer describe it as this. There are equal opposite charges on the plate, so there's no resultant charge, which is also true. Okay. So when you want to explain why this plate doesn't store charge, you can think of it as one side receives a certain amount of charge, that same amount of charge is repelled away, so there's no net change, no net accumulation of charge. That will be correct. But another way to explain it also will be based on this. The plates have equal opposite charge, so there's no resultant charge, so no net accumulation of charge. Also possible to explain it as that. This is how the marking scheme explain it. Okay, there are equal opposite charges on the plate, so there's no resultant charge. Okay, and then after that, why does it store energy? Work is done to separate the positive and negative charges, so energy is stored. Okay, this part here where you say work is done to separate the positive and negative charges, to separate charge from the positive and negative plate. This one I think you might want to reword it as this. Work is done to separate the charge from the positive and negative plates, so energy is stored. This one will make it easier for you to see. Okay, this part here refers to this part in your notes, the energy of your capacitor. This one here under page 5, where I explain to you why is it that your capacitor is storing energy. It's because you need to do work to overcome the repulsion of the negative plate and also to overcome the attraction of your positive plate. So if you want to write it so that it's easier for you to understand, you can just write this. Work is done to separate the charge from the positive and negative plates, so energy is stored. Then it will make much more sense for you. Okay, this part explains why energy is stored. This part explains why no charge is stored. Okay. Then after that, they ask you to define the capacitance of the capacitor. Okay. Now this one you see is 2 marks, and here they ask you to define capacitance of the capacitor. The capacitor here is actually your parallel plate capacitor. So when it comes to capacitance of a parallel plate capacitor, the definition is slightly longer. Okay, it doesn't follow this definition anymore. Okay, if it's just definition of capacitance in general, it doesn't relate to any specific thing. It's just ratio of charge to potential difference. But if it's capacitance that relates to something that's quite specific, like parallel plate capacitor, then you have to say this. It is the charge stored on either place of the capacitor per unit PD applied across the plates of the capacitor. Okay. Why do I say this? Is because you see, if you look back at this example here, for this capacitor, how much charge is seemingly stored by this capacitor? This charge seemingly stores Q. Okay, the charge that is seemingly stored by this capacitor is Q. But you look at what is stored, what is on each plate. This is negative Q, this is plus Q. Okay, so the charge that is seemingly stored is Q, which is magnitude-wise equals to the charge on either one of the plate of the capacitor. Okay, so that's why you get this. C is QV. The Q is actually the charge on either one of the capacitor plates per unit PD applied across the plates of the capacitor. Okay. Right. So this is a 2-mark question. Right. So if this is okay, then I will just move on to the next one. Okay, now the capacitor is charged so that the potential difference between the plates is V0. The capacitor is then connected across resistor for a short time. Is then disconnected. The energy stored in the capacitor is now reduced to 1/16 of its original value. Determine in terms of V0 the potential difference across the capacitor. So your capacitor is fully charged. They connect it to another resistor for a short period of time before they disconnect it. After they disconnect it, the energy stored in the capacitor is reduced to 1/16 of its initial value. So you can think of it as being something similar to this. Your capacitor is connected to your resistor. Your capacitor starts discharging. Okay, your capacitor starts discharging. So this one, your capacitor loses energy, discharging through resistor. Okay, your capacitor loses energy, so your Q and V will decrease. All right. So now they ask you, what is now the new potential difference across your capacitor once its energy has been reduced to 1/16 of its original value? Okay, so here you can actually just use back the same equation. E is equals to half CV squared. E is half CV squared. E is half QV squared. Or E is not half QV. E is half QV. E is Q squared over C. They want you to find the new potential difference across the capacitor in terms of V0. Alright. So here you can actually just use this one straight. I do not want to use this because this one has nothing to do with PD. I need to find PD here. This one has no PD inside, so this one I automatically take it off. And then this one here also has expression for PD, but I won't use this either because Q is unknown. I do not know the Q. It's unknown for both cases. Before discharge and after discharge, I do not know what is Q, so I cannot do anything with that. But this one, I can use. Alright, I want to find V. The C here is known. Okay, it's not exactly known now, but I know that the C does not change in both cases. Before discharge and after discharge, the C did not change. So this one is good to use. Compared to this one is not a good one to use because the Q before and after discharge, I do not know. Okay, so I will use this. E is half CV squared, C is constant, E is proportional to V squared. So E2 to E1 is V2 squared to V1 squared. Then I just sub in the values. The energy after discharge is 1/16, the original one. So this one is 1/16 E over E itself. They will cancel off. The original voltage is V0, so this one becomes V0 squared. So V2 squared is V0 squared over 16. Square root it, you get V0 over 4. Try to write it in number form now. This one is 0.25 V0. Most of the time, your final answers, they don't like you to write it in fraction. There are cases where they don't want you to write it in fraction. Here, the question allows you to write it in fraction. But if you want to be safe, don't leave it in fraction. Okay, you can, if possible, just write it as 0.25 V naught. Okay, right? So that one should be okay. You don't want to use ratio, you can use that same method as before if you wanted to. Just now you had a question like this, right? Where they say that your the one was under page 8, where they say that the calculate the PD once the energy is half its initial value, and then you use this method. Final energy is actually half your initial value, then you sub in and you find out the answer. You could also use that here if you wanted to, where your final energy is 1/16 of your initial energy. The method is still the same. You're still going to be using half CV square here. You see that they will cancel off, giving you your answer. All right. So it doesn't matter which one you use. You can use ratio or you can use something like this. It depends on your preference. Okay. Right. Before I continue, there's just something I need to highlight a little just now. It refers to what I just said earlier for your same question under page 28, this part here. Okay. I drew this one for you just now, and then I told you that what I mentioned was that a charge of negative Q will come, if this is your supply and this is your capacitor, a charge negative Q initially flows from here to this side of your plate. It gets deposited on this plate, causing this plate to acquire a charge of negative Q, and then at the same time, a charge of negative Q will be repelled off the other plate. So because this plate loses a charge of negative Q, this plate becomes positive Q. And then after that, I roughly mentioned to you that the charge seemingly, I can't see this one. Then after that, what I mentioned to you here was that the charge seemingly stored by the capacitor is Q, right? What do I mean by that is mainly because of this. If your capacitor, you assume it is fully charged right now, this capacitor here, you assume is already fully charged. Okay, when it's fully charged, and I tell you that you have negative Q and positive Q here, when it's fully charged, you take it out and then you put it through a resistor or filament lamp. Maybe here I tell you put it through a filament, maybe here I tell you put it through a resistor. What will happen is that when your capacitor is fully charged now, all right, your charges are separated. Here you gain a charge of negative Q on one plate, here you lost a charge of negative Q, so it becomes positive Q. So once you have it fully charged and you connect it to, say, a resistor or a filament lamp, this negative Q that you have here will start to flow out, passing through your resistor. Okay, then negative Q will start to flow out, passing through your resistor. So once your negative Q starts to flow out, this one will become neutral already. So the negative Q keeps flowing out from here to here to here to here until it eventually reaches here to the positive Q plate. Then this one and this one will cancel off. So now these two plates become neutral already. It has fully discharged. Okay. Now in the process of your fully charged capacitor discharging, notice that you actually have charge flowing through it, you actually have current flowing through it, but how much charge has actually flowed through is actually just really Q. Okay, even though here you say it's positive Q, negative Q, it doesn't mean that you have double the charge. It doesn't mean you have 2Q that is seemingly stored in your capacitor. It only means one. Okay, because the idea here is that whatever charge you have here, it will actually flow back to the other side. So the total charge that is actually flow is actually just Q. Okay. Now, and it is because of this that you get the impression that your capacitor is storing charge. Okay, that's why a lot of people, when they say what is a capacitor, they say it's used to store charge, but now we tell you it's actually not storing charge. The reasoning why we say it's not storing charge is because, as now I explained to you, whatever charge you gain here is the charge you lost here. So there's no net increase, no net accumulation of charge. But what your marking scheme wrote here was that this plate and this plate have equal opposite charge. So there's no resultant charge. That's also true. Okay. So it doesn't really store charge, but it gives you the impression that it's storing charge. It seemingly stores charge. The reason why it gives you the impression that it seemingly stores charge is mainly because of this. All right. Originally, when your capacitor is fully charged, your charges were already separated. There's actually no net increase, no net accumulation of charge. But once you connect it to a resistor, somehow or another, there's charge flowing through your resistor. It gave you the impression that your capacitor had charge stored inside. Okay, that's why a lot of people mistake your capacitor as having storing charge, when in the first place it doesn't. Okay, right? So just trying to digest that. Okay, now we'll just go back to page 11. This is another part of your notes. Sorry, another part of your worksheet. Go to page 11 of your, sorry. Okay. Right, page 11 is June 16 P41. Question 7. Question 7 has the graph plotting there, I think. Oh yeah, okay. If you look at page 11, okay, now they tell you a student sets up a circuit as shown in figure 7.1 to measure the charge on the capacitor for different values of potential difference across the capacitor. Okay, now the variation in potential difference V of the charge Q stored in the capacitor is as shown in figure 7.2. Okay, now you see this one, the question itself says that charge stored on capacitor. You see, sometimes the question contradicts themselves. When they ask you what is the function of a capacitor, they don't allow you to say that it is storing charge. But they themselves, when they describe the question, they say that charge is stored on the capacitor. Okay, so as I mentioned to you, charge is not actually stored on the capacitor. It is just seemingly stored on the capacitor. Okay, right. So back to this one. This one they tell you is the graph of your PD and charge stored on the capacitor. State and explain how figure 7.2 indicates that there's a systematic error in the readings of the meter. Now, how do you know that there's a systematic error here? Okay, they tell you the line does not pass through the origin. The charge should be 0 when potential difference is 0. That's correct. You see, your C is equals to Q over V. For a capacitor, C is equals to Q over V, right? When your potential difference is 0, maybe I better just write as Q is equals to CV. If your V is 0, by right, your Q should be 0. Right? Here, you see here, when your potential difference is, wait a minute, how did they say this? What here they tell you that even with your charge being 0, you're still having a value of PD. This one is not possible. Okay, if you have 0 potential difference, you should have 0 charge. It's only when you have a potential difference, then you have charge. But here, what this is telling you here is that even without a charge, you have PD. This is not correct. That's what this one actually means. Now, in the first place, how do you know the actual shape of the graph? You have to work out from this equation. C is equals to QV. You look at this graph here. This is a graph of Q versus V. Now, if this is a graph of Q versus V, you try to make this equation in the form of an equation of a straight line, y equals to mx plus c. So what you get is going to be something like this. Q is equals to CV. This one is y. This one is x. Q is CV, right? Yeah. So here, this one is your m. This one is your gradient. Okay. So by right, if you try to draw a graph of Q versus V, it should be a straight line that passes through the origin. Okay, right? So by right, you know that this one should be a straight line that passes through the origin if it follows properly. But what you see here is that if you try to draw a line of best fit, it clearly doesn't pass through the origin. And there's something like a zero error here. Okay, so here I know there is the presence of systematic error because I know for a fact it's supposed to be a straight line that passes through the origin. Supposed to be a straight line through origin, but here I don't see a straight line through origin. Okay, the ideal one should be this one. I think this one is better if I show it like this. The ideal one is this. This one is the ideal one. This one is the actual one right now. Okay. So from what you can see here, this one is your systematic error. Okay, the actual one should be a straight line that passes through origin, but your actual one is this one. So you have systematic error here. Basically, all the values are lower than the real value. Okay, systematic error was defined as when all your measured values are either higher or lower than your actual value, right? Or higher or lower than your real value. So here you can see that this is your actual measured value. This is your actual ideal. This one is actually the measured one, if you want to say this. Okay, so your measured values are all lower than your real value. Okay, so this is systematic error. So how you want to word it, you can just word it as this. Line does not pass through the origin when it should be passing through origin. The charge should be 0 when potential difference is 0. Or if you want to write, this one may be more suitable. The line has a non-zero intercept. The charge should be directly proportional to PD. That's also correct because you can see from here, Q is proportional to V. Okay, Q is proportional to V. Okay, so I know one of this. How do you know systematic error? Basically, you can just say line does not pass through origin. The charge should have been 0 when potential difference is 0. Okay, right, that part is fine. Yeah, and talking about this, I realized that I may have made a mistake just now in one of the questions. Just now, this one you see here where I say C equals to QV, and then I want to plot a graph of Q over V. I get a straight line that passes through the origin, but then my gradient is actually my capacitance. Then just now, when I talked to you about the energy of a charged capacitor, I tried to explain to you this graph, and I say it's C equals to QV, right? And then for some reason, I wrote that capacitance is also the gradient, right? I think I may have done some error there. If C is equals to Q over V, I want to change it to equation y equals to mx plus c. Y would be equals to 1 over c q. There was an error here, I think, just now. This was the error, right? I think I wrote it something differently just now. So if I want to change it to y equals to mx plus c, where y is the v and x is the q, the gradient is actually 1 over c. I think I wrote here gradient is actually your capacitance itself. Okay, that one was wrong. It's because I think I did some error here just now when I shifted it around. This one here is actually supposed to be y is v, that's correct. X is q, that is correct. Your capacitance is actually 1 over c. So your gradient is actually 1 over c. Okay. So just now I think I made a mistake here. I told you that your gradient is c. It's not c. It's 1 over c. There was a mistake that I made just now in changing the arrangement. Okay. So here, if you plot it as a graph of v versus q, gradient is 1 over c. But if you plot it according to what this question gave you, q versus v, the gradient is your c. Okay. This one here, gradient is your c. Okay. Right. Now the question asks you to determine capacitance in microfarad of your capacitor C. Right. Now you know that the gradient is your capacitance C, so they ask you to find the capacitance microfarad of your capacitor C. All you just need to do is you draw a line of best fit, find out the gradient. The gradient would be your C, as proven here already. Okay, let me just wipe off this part here. Okay, if you use C equals to QV, you try to change it to equation of a straight line where Q is Y, V is X, you eventually get to the conclusion that your gradient is actually your capacitance. So here they ask you to find capacitance of your capacitor, just find the gradient. Okay. But in the first place, you did not have the lines, so they expect you to draw the lines. Okay. Your graph, your question paper did not have the line of best fit. You're expected to draw the line of best fit yourself. You can clearly see it forms a straight line, so you need to draw your own line of best fit. If you draw your line of best fit, they see that you've drawn your line of best fit, you get 1 mark there. And then after that, you find your gradient, the gradient being your capacitance, that is your other mark there. Okay. Use gradient to find is 1 mark. Actual correct answer, another mark. Okay. So that one should be okay. Is there a range of answers for this? Let me just check for you. Gen 16 P41. Okay, wait on. Gen 16 P41. Is there a range of answers? Question 7, right? Yes, there's a range of answers. Your capacitance should be within this range. 2800 plus minus 200 microfarad. Okay, you should have a range to your answers. It will be 2800 plus minus 200 microfarad. So in other words, if the range of your answer is between 2600 to 3000 microfarad, your answer is correct. Okay, so just find from there. Okay, Then use your answers in B to determine the additional energy that will be stored in the capacitor when the potential difference in it is increased from from 6 volts to 9 volts. How much increase in energy will you get in your capacitor when you increase the PD across it from 6 to 9 volts? Okay, so in your case here, you have mentioned of V, you already found your value of capacitance. It's easier to just start with E equals to half CV squared. Okay, so as I mentioned to you, when you're talking about energy of capacitor, it can be half QV, half CV squared, or half Q squared over C, right? So what you have here is that you know C and you know V, so it's easier to use this. Okay, so what is the increase in energy? It's basically half CV2 square minus half CV1 square. Okay, and as I mentioned, the capacitance value does not change regardless of whatever you do. Only your voltage and your charge will change. The capacitance value itself will not change, so you don't need to do anything. Okay, so your new voltage is 9, your old voltage is 6. So just sub in your values and calculate out and you get your answer. Okay, now be very careful about when you do this kind of things. Half CV2 square minus half CV1 square will give you half CV2 square minus V1 square. Okay, now I've seen some candidates, they do this. They say that V2 square minus V1 square is the same as V2 minus V1 square. This is not correct. Okay, so you don't take 9 minus 6 and then square out the value. It is not the same as 9 square minus 62 square. Okay, this is from your maths, you remember, where we tell you a square minus b square is not the same as a minus b square, because a minus b square is a square minus 2ab. Wait, yeah, because a square minus b is a plus b, a minus b, I think, and then this one is a square minus 2bc plus, sorry, minus 2ab plus b square. So you're not going to get the same thing. All right, basically it's just this now. All right, this one is not the same as this. Okay, so don't do that. Okay, right, so this one is page 11. If you're okay with that, then you can go on to page 14. Okay, I'll go on to page 14 here. Okay, so go to page 14 if you're done with this one. This one will be the next one. Okay, now page 14, June 16, P42. Question 7 again. Okay, right, so this one I'll clear off this part. Now, state 2 uses of capacitors in electrical circuits other than for smoothing of direct current. So what are the functions of your capacitor? You can say it's used to store energy. You can say it's used to block direct current. Okay. You can also say it's used to smoothen the rectified AC or to smoothen a direct current. This is actually under your AC circuits chapter. Okay. The more the other common functions, the other common use of your capacitor, you can say is as storing energy or to block direct current. Okay, but as mentioned to you before, don't ever write that your capacitor is used to store charge. It doesn't really store charge. Okay, right. Now the part where you say that your capacitor is used to block direct current is this. You see, I mentioned to you that when your capacitor starts charging out, if you have a charge of negative Q coming out, that negative Q will be deposited at this plate, and then that same negative Q will be repelled away. So during that process, this plate becomes negative Q, this plate becomes positive Q, right? So the thing here is that when your capacitor becomes fully charged, charge will no longer flow. It won't flow from here to here and here to here. Okay, your charge will only continue flowing. In other words, your current will only continue flowing when your capacitor is not fully charged, because that time you will still have differences in potential here and here, here and here. So you will still have current flow. But when your capacitor becomes fully charged, I mentioned to you last week, the potential here and here will be same. Potential here and here will be the same, such that the PD across here will be the same as the PD here. Okay, so when your capacitor becomes fully charged, no current will actually flow already. That's why we can say it is blocking direct current. You can use it to block direct current. The current will actually stop flowing when your capacitor is fully charged. Okay, so that part is okay. Now, the combined capacitance between terminals A and B of the arrangement shown in figure 7.1 is 4 microfarad. Two capacitors each have capacitance C and remaining capacitors each have capacitance of 3 microfarad. The potential difference between terminals A and B is 12. Find out capacitance C, which is this one here. Okay, how do you find out the capacitance here? Okay, you can try to simplify this circuit. How you want to try to simplify this circuit is by thinking it as this. Now, this one here for the parallel combination, is correct to say that I can simplify this one to become this, right? Where this one becomes C, this one becomes C. This one, they're connected in parallel. They will be having the same form as resistance in series. So this one, I need to add the capacitances together. So this one will be, if this is 3 microfarad, this is 3 microfarad, this one should be 6 microfarad, right? Okay. So what I do is I try to simplify this circuit. The easiest one for you to simplify is this one first. Because they're connected in parallel, you can just add them up like you would resistors in series. So this one becomes 6. Okay, then from there, you simplify further this one. Okay, for your whole circuit, this one is connected in series. The capacitor is connected to series. You add them up as you would resistors in parallel. So 1 over C CT is actually equals to 1 over C plus 1 over C plus 1 over 6. Okay. Your CT here, your total capacitance, has already been given to you as 4 microfarad. Here they already told you that your total capacitance between terminals A and B is 4 microfarads. In other words, what they say is that this is equivalent to this, whose total capacitance is 4 microfarad. Okay, so then you get this. Total capacitance is 1 over C plus 1 over C plus 1 over the parallel component, which is actually 6. So it's 1 over C plus 1 over C plus 1 over 6. Total capacitance is 4, so it's 1 over 4. So solve for that, you get your combined capacity, you get your capacitance C as 24 microfarad. Okay, right. So this part should be okay. Now then calculate the magnitude of the total positive charge transferred to the arrangement. Okay. Now calculate the magnitude of the total positive charge transferred to the arrangement. The word positive charge here doesn't really mean much. It's actually just your charge Q that is transferred to the arrangement. What do I mean by that? Is this, you see, if I again use back that same example that I drew just now for you, if here I have negative Q, negative Q, negative Q, that negative Q will be deposited on this plate. The same negative Q is deposited away. Okay, so this one here will become negative Q, this one here will become positive Q. Okay, so this part you understand from there. If say I do it the other way, if I tell you a charge of positive Q comes, positive Q, positive Q, positive Q, this one is, I assume, negative charge flowing from the negative terminal. If I assume positive charge flowing from the positive terminal, positive Q comes from here to here, going to this plate, it gets deposited on this plate, then the same positive Q is repelled away, it goes on to the other side. This charge, gaining a charge of positive Q, will mean that this side will be positive. Wait, let me use a different color. This plate itself will become positive Q. This plate, having lost positive Q, will become negative Q. Okay, so now here they ask you the magnitude of the total positive charge transferred to the arrangement. Even though they say total positive charge here, it doesn't really mean anything much. It is just simply talking to you about what is the charge Q that has been transferred. If let's just say they ask you the total positive charge that has been transferred to the arrangement, it is actually just talking about this Q. Okay, which magnitude wise will also be the same as the ones here if you consider for negative charge. All right, so the capacitor here, they ask you to find out the total positive charge. Total positive charge, this one they tell you total capacitance is 4 microfarad. Your PD is 12 volts. When they ask you what is the total positive charge transferred to the arrangement, it is just asking for you about what is Q. All right, it doesn't matter whether you're referring to the negative Q flowing or the positive Q flowing. It is just referring to Q itself. Okay, so you don't really need to bother so much about the wording positive. Okay, so in your case, they want the total positive charge transfer to the arrangement. You consider the whole circuit simplified already, where the total capacitance is 4 microfarad. Okay, and the total PD is 12. What is the total charge that is actually transferred? Okay, the total charge that is actually transferred, if this one is Q, this one is Q, this one is Q. The total charge that is transferred is, you are able to calculate it from C equals to QV. Q is CV, C is 4 microfarad, V is 12. So you know that your total charge traveled is 48 microcoulomb. Okay, right, this is the total positive charge transferred to the arrangement. Okay, so the positive here doesn't really mean anything much. You're really just interested in the magnitude of the Q, that's all. All right, whatever Q you get here will also be the same Q that you get here if it's talking about flow of positive charges. Likewise, whatever Q you have here will also be the same as the Q that you have here if you're considering the flow of negative charges. All right, it doesn't mean anything much. Now use your answers in 2 to state the magnitude of the charge on one plate of capacitor or capacitance C, and capacitor or capacitance 3 microfarad. What is the total charge that is stored here? Now for your case, this one, it will be easier to see from here. Just now it was mentioned that if your total capacitance is 4 microfarad, Oh, sorry. Your capacitance is 4 microfarad. There's a mistake here. It's 4 microfarad, and your total charge transferred is 48. This one I can break it back down to this one, right? So in general, I know there's 48 microcoulombs flowing, 48 microcoulombs flowing, but at this junction here, the charge will split up. Okay, they will split up equally because the capacitance value is the same. So this one will become 24 microcoulomb. This one will become 24 microcoulomb. Okay. So I know that originally when I simplify the whole circuit with total capacitance 4 microcoulomb and total PD of 12, the total charge that is being transferred through the whole arrangement is 48. Now they're asking you to find out what is the charge stored, what is the charge transferred for specific capacitors inside the circuit, for capacitance C and for capacitance 3 microfarad. So you can see from here. Okay, capacitance C will only have 48 microcoulomb transferred. Capacitance of 3 microfarad will have 24 microcoulomb. It will take half, because here you can say that capacitance is the same, so charge is divided equally between them. Okay, right? So that part is okay. Then this one is done. Right, so this one is okay. Then you can have a look at page 21. Right, so have a look at page 21 if you're okay with that already. Okay, this one is I think somewhat similar. Go to page 21. This one is page 21. Just go to page 21. Okay, go to page 21. This is November 16 P42. Okay, now define capacitance. Capacitance here, I don't think I need to explain this. This one is just ratio of charge to potential, ratio of charge to potential difference. That's all there is to it. This is a general definition worth 1 mark, so you just use this. Okay, right. Then after that, for part 2, they asking you to use the expression for electric potential due to a point charge to show that for an isolated metal sphere of diameter 24 centimeter, it has a capacitance of 1.4 times 10 power minus 11 microfarad. Okay. Show that capacitance of a metal sphere is equals to this. And when you want to show that, you need to use the expression for electric potential due to a point charge. So it's basically asking you about capacitance of a charged sphere, which you know is 4 pi epsilon naught r. How do you know is this one? I mentioned to you, you need to first know that potential due to a sphere is this one. V is equals to 1 over 4 pi epsilon naught Q over R. And definition of capacitance is Q over V. So V you sub inside, you will eventually get this expression. So from there, you sum up all your values, you'll be able to find out the capacitance of your sphere already. Your epsilon naught is from your first page, sorry, it's from your second page, it's from your data sheet, which is 8.85 times 10 power minus 12. This is epsilon naught. Okay. Your R here is your radius. They give you diameter 25. So you need to divide by 2 to get radius. So you get your answer as 1.4 times 10 power minus 11 farad. Okay. So this one should be okay. Then after that, you just look at part B. 3 capacitors or capacitances 2, 3, and 4 microfarad are connected as shown in this figure to a battery EMF 9 volt. Find out the combined capacitance of the 3 capacitors. This one, you can try to simplify it. You see this one and this one is connected in parallel. You can add them up together like you would resistors in series. So this one will become something like this. This one will be 3 microfarad. This one will be 6 microfarad. Then from there you can simplify it further again. The capacitances in parallel was 4 plus 2 giving you 6. So this is now your new equivalent circuit. So they are just connected in parallel. They are connected in series. When you want to add them out, you add them like you would resistors in parallel. So 1 over 3 plus 1 over 6, giving you total combined capacitance of 2 microfarad. So far so good. Okay, so this one is okay. This one in turn can be simplified to become this, where your combined capacitance is 2 microfarad. Okay, so in this one is okay. Then you go to the other one. They are asking you right now the potential difference. Find out the potential difference across the capacitance, across the capacitor or capacitance 3 microfarad. Okay, now you want to find the potential difference V across this one. You know C is equals to Q over V. You know capacitance. You want to find V, but you're missing Q here, right? Now the Q here, you can find it out after you have simplified this circuit even further. You see, this one can be simplified to this, and then this one can be further simplified to this. Okay, whatever charge that is flowing through here will be the same charge here and here also. What I mean is that if you say that Q is flowing like this, whatever charge that is here will also be the same charge here and here. Okay, so Q, 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 and Q. Okay, so what you want to do now is that you want to find out this charge here first, so that later on you can apply it over here and find out what is V. That's what you're trying to do here. So here, your total PD from your diagram was 9 volts. Okay, your total capacitance is 2 microfarad. You apply C equals to QV, but for the entire circuit. So the total charge that you have flowing is 1.8 times 10 power minus 5 coulomb. So that charge here is also the same charge that will flow through this 3 microfarad. So here you also apply C equals to Q over V again, but specifically only for this capacitor, right? So capacitance of 3 microfarad, charge of 1.8 times 10 power minus 5, you get your voltage as 6. Okay, that's how you do this particular question. Okay, and then the last part here would be find out what is the capacitance, sorry, what is the charge stored on the capacitor or capacitance 2 microfarad. So as I mentioned to you, the positive here, you don't really need to bother so much. There's actually just asking for you about Q. That's all, the magnitude of the charge, that's all. It doesn't matter whether they're called positive or negative. You're just really interested in the Q, that's all. Okay, find out the positive charge that is stored on the capacitor or capacitance 2 microfarad. This one is referring to this one here. Okay, so here this one, you know that this is equivalent to this in turn is equivalent to this. Okay, now whatever charge that is flowing Q here is the charge flowing through here also. That charge is also the charge flowing through here. But this one here, when you consider it, you see it as this. This one is Q. This one is Q. This one is Q. And then once it reaches this junction, it will split up. Okay. But the thing here is that you see this capacitance and this capacitance are not the same. So your charge here, when it splits up, you cannot say that they will be splitting up equally. It is different from the previous question that you've done. The previous question that you've done just now, the two capacitances here are the same, so your charge will split up equally. But for this question that you're doing, the two capacitances here are not the same, so they won't split up equally. So I cannot say that this is Q over 2, this is Q over 2. It's not as straightforward as that. So this one is maybe Q1, this one is Q2. You want to find out what is the charge flowing through these 2 microfarad capacitor. Okay, so you can use C equals to QV for this one again, but you're missing some information, right? You know the value of C. You want to find the value of Q. This is what you want to find. You can only find the value of Q if you know the value of V also in the first place. Now, here is where the previous thing you've done will be helpful. You already found out the capacitance. You already found out that your capacitor of 3 microfarad has a PD of 6 volts. From there, you can work out what is the PD across here. You see, just now you already found out that the 3 microfarad capacitor has a PD of 6 volts. So you apply Kirchhoff's second law from here all the way to here, you come to the conclusion that this one here is going to be 3 volts. So you also have this already. So you have C, you have V, you can now work out to find out what is your Q. So you can just use this equation again. V is 9 minus 6, giving you 3 volts. That is the PD across your 2 microfarad capacitor. You use Q equals to CV, use the value of the capacitance, use the value of the PD, you find out the value of your charge is 6 microfarad. Okay, so that should be it.